Hi everybody. I'm gonna let this run just a little bit because it looks like there aren't that many people in here yet. So just kick back and get a glass of water or coffee or whatever it is you're drinking, and hang out for a bit, and we'll get started soon. All right, I am back from the clinic that I had to go to yesterday because of back issues. Maya's also here. She says hi. Say hi, Maya. Maybe you could hear that. I don't know. So administrivia and stuff like that, since I have like 3 days of announcements to catch up on. um, we were supposed to do a lab lecture this week, but the lab lecture was canceled because I felt that the lab was pretty self-explanatory. In fact, almost all the labs that we do in 131 are test for these things, tell me if this is what you have, and you've seen one, you've seen them all. So the third one, which you're going to do this week, is more or less just like that, but with more tests. I would encourage you to get together either in the Discord or over email or Zoom or whatever it is that you crazy kids do these days. And discuss what you think the answers are, because this is definitely open to some interpretation, but there is one intended best answer that I'm going to grade you on. So yeah, so that's the lab. Tuesday, we were supposed to do this chapter that we're going to start right now. I woke up in the most pain I've ever experienced ever before, and I thought that I was going to be stuck. Like, I couldn't even move. And so I called a friend, and he helped me get to the clinic. And, I mean, there's not really much else to say other than, like I had a back injury or something, and so now I have some muscle relaxers, and I should be able to do my job. But yeah, one of the joys of getting old is your back goes out. And by old, I mean 37. So you have that to look forward to. As for the missed lecture, I'm not going to do an extra stream that you'll have to watch on your own time. What I'm instead going to do is I'm going to turn one of the Q&A days. We'll just make it a lecture day. We can't do that next week because I think next week is President's Day. So it will probably be week 8 where we'll just have another lecture, and then we'll be all caught up by then. Or maybe we'll go so fast that we'll catch up to where we're supposed to be or whatever. I don't know. So that's where we're at. And let's get ready for the last chapter of chemistry, or organic chemistry anyway. Because after this is biochemistry, and the biochemistry chapters are very different. But who's not different? It's Maya. Where is Maya? I just heard her. I don't know. All right. Look at all these sections. Oh my goodness, that's so many sections. We're going to talk about new functional groups in this chapter. The focus is on organic acids, bases, and derivatives. So this is the part of the quarter where you need to know what pH is. So pH being a measure of acidity. Low pH means that there's lots of H+. High pH means there's very little H+, because there's a lot of OH-. The two primary groups we could group these into: carboxylic acids, duh, it has acid in the name, it must be an acid, right? Are acidic. And then amines down at the bottom are basic. And they sort of do the opposite things to each other, but they have very similar interactions in some regards, particularly the functional groups that we make out of them. So we're going to talk about those functional groups here. So you've already seen this functional group because this is the product of oxidizing an aldehyde or a primary alcohol all the way to as far as it'll go. It's called a carboxylic acid. Carboxylic acids contain the C double bond O OH group. When it's written in shorthand or linear, we just write -COOH. The other functional group that we're going to look at in the acid section is called the ester. An ester contains a C double bond O, and then instead of OH, it has OR on it. Don't worry, we're going to go over... Oops, I don't know why that didn't show. Oh, probably because part of it got pushed off the screen there. We're going to go over all the naming one step at a time, because there's a lot of crazy different naming schemes. And they're not terrible, but they are different. So, whenever you see this C double bond O and then an O adjacent to it, you should think, okay, carboxylic acid or ester. And if the O is attached to an H, it's the acid, but if it's attached to an R, that's the ester. Now, later on, we're going to replace this O right here. I don't have the pen out. Hold on. We're going to replace this O right here with a nitrogen, and that's going to be an amide. So esters and amides look very similar to each other. Now, I think the most confusing groups to remember are these two. So we've got the amine. An amine is any group that has nitrogen on it. Now, you'll notice that there's an electron pair here on my nitrogen. That's important. Remember that if I have a nitrogen atom and I draw all its Lewis electrons here, like that, nitrogen's in group 5 and it has 5 valence electrons. Hopefully you remember that from 121. These unpaired electrons can go bond stuff, whereas this lone pair just sits here. That lone pair is going to be very important later on because it can be used to react with things like H+. So when we talk about basic properties of ammonia and amines, that's where this is going to come from. Now, an amine is just any nitrogen that has a bunch of single bonds coming out of it. We're not going to study any nitrogen double bonding groups, so no imides, no imines, nothing like that. But amines and amides and all the nitrogen-containing groups all sound exactly alike, so be very careful. So amines have just nitrogen by itself. Amides have C double bond O connected to N instead of C double bond O connected to O. We're going to do all of these groups one at a time. We're going to start with the acids part. So we're going to do carboxylic acids. And then we're going to do esters, because you make them out of carboxylic acids. And then we'll work on amines and amides later. We're not going to get to those today, but that's okay. So let's get started. Let's do the first part. That's going to be carboxylic acids here. First, we got to talk about how to name them, and you already know how to make them. You oxidize an aldehyde or a primary alcohol. So that part's not going to be super exciting. We're just going to talk about naming stuff. So when you are given a compound, this is going to be your functional group that you're going to look for. And because you need C double bond O and then an OH to see a carboxylic acid, you're always going to have a carboxylic acid on the very end of a hydrocarbon. So just like aldehydes, naming them is going to be fairly straightforward in the sense that, oh, I don't have to number the position. In fact, that carbon right here in my carboxylic acid is always going to be carbon number 1. And then you would just number the carbons based on that and then name the hydrocarbon chain like you normally would. So let's look at an example for that. Oh, well, first let's talk about the one common name that I actually expect you to know. So there are a lot of carboxylic acids out there. In fact, carboxylic acids are so common that people studied them before we had actually developed the naming system. The only one that I care about that you know is acetic acid. Acetic acid is also known as vinegar, and I'm going to write its actual IUPAC name on the board here. So this is the official name for it, ethanoic acid. Wait a second, hold on. This isn't acetic acid. I'm not sure why my structure looks like this. Hold on. This is totally bogus. There's way too many carbons on here. Hold on. Boop. Boop. Wow, how bizarre. CH3COH. Yeah. Okay. Oops. Oh, I hate that sound. So when I'm drawing my structures, if I ever make a mistake, that's what I hear. And it's just like, stop that. So I'm just editing the structure, which is why you can't see anything right now. Let me hit save real quick. And then, there we go. That's what it should look like. There's an extra carbon on there. That was propanoic acid on there for some reason. So let's write that on there again. Oops. If only I had someone to proofread my slides for me. I can only catch so many of these mistakes. There we go. Acetic acid and vinegar. Now, excuse me. You might notice that, well, hold on, ethanoic acid looks a lot like ethane. Is there an ethane in my acetic acid here? And yeah, it's right here. So just by looking at this, you've probably already sort of determined the naming scheme for carboxylic acids. You just take whatever the hydrocarbon is and add oic acid at the end. And there you go. That's how you name a carboxylic acid. Now, if you see something referring to acetic acid or acetate, that's what this is. This is vinegar is so common that everybody just calls it this instead of ethanoic acid. So that one is worth committing to memory. All right. Naming just like before. Find the longest chain with the carbonyl C in it. And then instead of naming the chain as it is, what the heck? Why are my examples? So this is also wrong because there's 5 carbons here. Hold on just a second. Who did I get these slides from? Ugh. Okay. There, I fixed it. If you're confused, maybe it's because my slides are garbo in this chapter, and I'm finding all these mistakes. Ugh. I apologize. Oops. All right. So, just like naming any hydrocarbon before, we're going to identify the longest carbon chain that has this C in it, this C double bond O. That carbon is part of the chain. And then what we're going to do is we're going to count the number of carbons in that chain. 1, 2, 3, 4. So there's 4. So normally we would call something with 4 carbons butane. But because it has a carboxylic acid in here, what we're going to instead do is we're going to cross out this E and add oic acid on the end. And there you go. Now, if there are groups coming off of here, you name them too. So, like if I had a Cl over here or something like that, then I would go, okay, well, this is 1, 2, 3, 4, 4-chlorobutanoic acid, for example. All right, so I'm going to give you some very simple ones. However, this one down here is special, and you may have forgotten all about it, that it exists from the chapter where we talked about benzene derivatives. So if you remember it, type it in the chat. That's great. But other than that, these other two you should be able to name pretty easily. So go ahead and name those in the chat once you come up with their identity. And then we'll go over the answers together. These structures are correctly drawn. There you go, you found it. That's right. Benzoic acid is the bottom one. All right, we'll go over the answers in just a second. One more minute. All right, let's go over the answers here. So we're going to number the carbonyl carbon as number 1. So there we go. So we'll go 2, 3, 4, 5, 6, 7. So this is a heptane. And I'll go like this. And it's carboxylic acid, so I'll add oic acid at the end, and there you go. There should be a space in here. It's kind of hard to see. Ow. Okay, I guess I could write it again. There we go. The button between eraser and erase all ink on slide is it's very easy to misclick them because they have the same icon basically. This down here is benzoic acid. Benzoic acid is a very special type of benzene derivative that the functional group that connects to the carbonyl is just a benzene ring. And then finally over here, if I number my chain, on carbon number 2, I have a methyl group, so we would just say 2-methyl. And then this is a propane, because it's a 3-carbon chain, but it's also a carbic acid, so we'll say carboxylic acid, so we'll say 2-methyl propanoic acid. I don't know where that little dot came from. Let me not hit erase all this time. Now you'll notice that there is a space between oic and acid in all these cases. So make sure that you are putting that space in there when writing the answer and not just writing carboxylic acid as one word. It's very rare to have spaces in naming organic compounds, but carboxylic acids will have spaces. Esters will too. All right, any questions, let me know. All right. And like I've said probably like 4 or 5 times today, how do you make a carboxylic acid? Well, you take your primary alcohol and you go, boop, oxidize it. Now it's an aldehyde. Boop, oxidize that. And now it's a carboxylic acid. Hooray! We already knew that. I tested you on that. That's the way to make carboxylic acids. Now, what can we do with carboxylic acids? That's going to be in the next section here. So we'll go over that in a very short order, actually. It's too hot in my office. I had to turn the heater off. And that's why I'm stretching to reach the thing, because it's on the floor. All right, let's talk about physical properties first. Are carboxylic acids soluble, and what are their melting points and freezing or boiling points? Because that's what we care about these compounds. So, shown on the screen here, I have 2 carboxylic acids that have arranged themselves in such a way that the OH group points at the carbonyl oxygen on another copy of the carboxylic acid, and then the reverse happens up here. Let me erase that line here and redraw this so it's consistent. So this OH is pointed at this O right here. And so what I end up having are 2 molecules that are sort of just holding on to each other. Now, because carboxylic acids can do this, they can hydrogen bond to themselves, and hydrogen bonding interactions are strong. They can hydrogen bond to themselves or others and just kind of make this really long chain if they wanted to. Their boiling points ends up being really, 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 really high. In fact, the boiling points for carboxylic acids are so high that the bonds end up breaking, like the chemical bonds, end up breaking before the intermolecular forces do. And so what you end up having is an event called decomposition. If you heat these up too high, what ends up happening is that they just fall apart. They react with the oxygen at that high heat and become like CO2 or other various products. It's basically the same effect as setting them on fire. Like, that's how hot they have to get in order to get to where they should start boiling, and instead they just combust and do other random things. So this can happen to some molecules that are just particularly stable. As they decompose, they fall apart. So carboxylic acids have extremely high boiling points. Now, if they can hydrogen bond with themselves, certainly they can hydrogen bond with water, right? Of course they can. So carboxylic acids are soluble in water to a high degree. If you have 6 carbons or less in your carbon chain, or counting the side groups too, so a total of 6 carbons, that carboxylic acid will be infinitely soluble in water. You can dissolve all that you want. So, for example, vinegar is completely soluble in water. You will never form a second layer or an insoluble solid with vinegar. Going past 6 carbons or so, the solubility goes way down. So 6 is quite a lot of carbons. Remember that for alcohols, you could only get like 3 or 4 in there. But that extra oxygen provides more opportunities for hydrogen bonding, and so it makes it more soluble. All right, that's really all there is to physical properties for carboxylic acids. The sort of borderline physical/chemical property is where we get into the interesting stuff, and that's acidity, which is what we're going to... I guess that's on the next slide. Yeah, there we go. Well, let's summarize boiling points. Pure acetic acid is a solid at room temperature. I would believe that, yeah. So if you had just pure acetic acid, it would hydrogen bond to itself and be a solid. But it's super, super soluble in water, and we don't really obtain it as anything but a solution. So let's arrange these by solubility and boiling point, and you're going to notice that the order is more or less the same. So now that you have seen all of the oxygen-containing functional groups, we can arrange them all together. Remember that aldehydes and ketones are roughly the same polarity, so they're going to be roughly the same in terms of these properties. But we can arrange these by intermolecular forces. So we've got dispersion. And more or less, ethers are also dispersion. They're a little bit polar. Then we have dipole-dipole. And then we've got hydrogen bonding. So this is what I hear. That is what I have to deal with when teaching. You can't hear her, but all I hear is meow, 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 meow. Maya, please. She misses you guys. All right. So there's our arrangement and the reasons why. So dispersion forces are weak, dipole-dipole interactions are stronger, and then hydrogen bonding is the strongest. Now, again, this is typically for molecules that have a fairly low molar mass, or at the very least, when they all have about the same molar mass. So if I compared hydrocarbons and carboxylic acids with the same molar mass, this would be the rough ordering. All right, now that I've pet Maya, oops, I pet her ear, and that made her annoyed. She's now rolling around on her book. All right. Let's talk about carboxylic acids and their acidic properties. Now, the OH, this H right here, is the acidic hydrogen. And what that means is that that bond between the O and the H will split. And when it splits, it does so in this fashion. So here's my O. I'm going to draw the electrons in here. And my H. When a carboxylic acid dissociates, these electrons in the H, the OH bond, get returned to this oxygen. And the result that we get is this. So here's the electrons that were there before. These two electrons got returned in a pair. and then my H is by itself. But if you think about this in terms of how many electrons these started with, normally H would just have one electron, but here it has nothing because both electrons got returned. Since I have a fewer electron than I started with, I assign it this symbol. Likewise, with the oxygen, oxygen would normally have 6 valence electrons going on around it. Now, if we assume that this one over here is still shared, I would have 1, 2, 3, 4, 5, 6, 7 around it, which means that I would assign oxygen this symbol in this exchange. So when I split my OH bond, I don't share the electrons. The oxygen just says, these electrons are mine now. We are no longer in need of your service. And the hydrogen leaves as H+. Now, typically what will happen is that this will bump into water, and you end up with this. And this is called hydronium, which hopefully you have seen before in Chem 121. Now, for our purposes, hydronium written as H3O+, or as H+, these are equivalent. You could write either one, and in fact, I'm probably going to write H+ most of the time, just because it is shorter to write. All right, I'm sure that this is going to appear as a picture, so I'm going to clear my slides. There we go. So here's some carboxylic acid reacting with water. This H hops over here as H+. And what I am left with is this O-, and my H+ is moved over here to make H2O into H3O+. In this exchange, charge is conserved. So it's at the start I have no charge. Then I create a charge by splitting a bond. When I split the bond and give the electrons back to oxygen, not when I split the electrons equally, I'm splitting them unequally, oxygen becomes negatively charged and H3O+ becomes positively charged. And so this is called an acid. This is what acids do, is they deprotonate themselves and the H+ goes somewhere else. Now, this reaction is really, really reversible. So what that means is that at any given time, most of this, so like 99% or more, is what this is. And this over here is a very, very, very small amount of the solution. Yeah, more reaction sheet reactions. Get that reaction sheet out. The fun don't stop because we're in the second quarter or half of the class. So this process is called dissociation. When a carboxylic acid loses its H+, it becomes dissociated. Because here are the two components. They're not bonded together. They're dissociated. Now, if you recall from 121, we talked about a property called the Chatelier's principle that said, well, if I have a system at equilibrium and I change the conditions around it, the amount of each thing will also change. So, for example, if I have a carboxylic acid and water and they dissociate, I could add or remove water and that would affect the concentration of all the other species. Or I could add or remove a source of acid and that would affect the presence of all species in the solution. Maya, please. Oh, she's leaving now. Okay. So let's do an example of that. Let's suppose that I increase the amount of H3O+. So if I increase this, then I have too many products. And in terms of the equilibrium, if I have too many products, I have to get rid of them. I have to consume them in some way. And so the reaction will shift left and turn products into reactants. What that means is that if I say have, like, I don't know, 0.1 moles per liter of this carboxylic acid, and I increase this number will go down, and this number will go up. So hopefully we remember Le Chatelier's principle a little bit. If you disrupt equilibrium, you can change the amount of stuff, both products and reactants. Now, if I do this the other direction, for example, let's suppose that I take my H3O plus and I remove it by adding a base or something. So I decrease the amount of H3O plus in there. Then what ends up happening is I have too few products. Because I removed them all, right? I removed all of this. If I have too few products, I have to replace them with the equilibrium. So the equilibrium will shift in this direction to turn reactants into products. Another way of thinking about this is that the reaction tries to undo what you just did to it. So, for example, if I removed all of this acid, then the reaction will dissociate and make more of it. If I were to fill this with acid, then that acid's going to find my carboxylate, and then it will produce more of the carboxylic acid form. The takeaway for this is that if your pH is low and you have lots and lots and lots of acid in there, this is mostly what you have. If your pH is high and you have very little of this, you have mostly this in your solution. And that makes sense because if I threw in a carboxylic acid and a base at high pH, this should be the result, right? The base should react with this thing. Now, carboxylic acids are common enough that you find them in the body. In fact, one of the most common carboxylic acids is H2CO3, which is carbonate. Actually, is carbonic acid going to be considered a carboxylic? Because it has two OHs on it. I'm not sure. It's close enough, we'll say. So carbonic acid is like a carboxylic acid, but it's got two OHs on it instead of just one. What are other common acids in the body? Probably like citric acid. Oh, it says it right here in front of me. God. So this is a common carboxylic acid that is found in things like citrus fruit. And so like lemon and stuff, this is where I was going in my head before I just read the screen in front of me. Lemon or orange or grapefruit or things, these are all really tart because they contain acids. Acids tend to be very sour. HCl is not a carboxylic acid because it doesn't have a carboxylate group in there. There's no carbon. But it's definitely an acid. Now, if you measure the pH of things like citrus or lemon or grapefruit or whatever, you get a pH that's fairly low. So, like, the pH of a lemon is around 2, 2.5, something like that. Let's go to this slide over here. in a lemon or a fruit, you would have mostly the undissociated form. Because, so if I draw my carboxylic acid, we'll put R here. At pH 2, we would have lots of acid in the solution. And so that would drive my equilibrium in this direction. So if I have a lot of this, I'm going to use it up to recombine and get this. So in fruit and citrus, you mostly see citric acid like this form. Now, let's suppose that you were looking at a higher pH, so like pH 9 or so, for example. That's not how you spell little. There we go. So at a higher pH, there's very little H plus in there. So in other words, at high pH, this is low and is not abundant. It's just gone. So in this case, the reaction would move in this direction, and you'd have mostly the unprotonated. There we go. Oh, my thing is hiding over there. Let's see. There we go. So if the whole idea of Le Chatelier is just kind of over your head and you're like, oh man, I don't remember this. Two things you can do. One, you could go back and review unit 8, I believe. 8 or 9. From the previous quarter's text. So you should have your notes probably still. Don't ever throw away your notes. I have all my notes from college. Sometimes I even still look back at them, like, because I need to. Or what you can simply remember is that at low pH, you have mostly the undissociated, and at high pH, you have mostly the dissociated. Now, let's talk about a biological system such as your body. Your body has a bloodstream in it, and the bloodstream has a pH of about 7.4. What that means is that you have slightly more of the dissociated form than you would expect in, say, pure water. Now, does that mean you have slightly more of the dissociated form overall? No. Remember that at normal conditions, we have way less dissociated than associated. And that's due to the equilibrium constant, which is what I showed you earlier. Now, another thing to note is that sometimes you will hear the word, or at least the suffix, ate. Like you might hear acetate instead of acetic. What that ate means is that is the dissociated form. So if you have benzoic acid, you would have, let's go back to this screen right here. If I had benzoic acid, this would be what I have. So there's the benzoic part, and there's the benzoic acid. But you might have heard of this compound because it's a preservative. I think I have a slide about this in a little bit. If you see this 8, what you should think is, oh, okay, what is this part? That's this thing over here, right? So you would draw that. And then instead of writing OH, you'd write O minus. And then the sodium, if you check ingredient labels, if you check chemical bottles, Oh, excuse me. If you check the slides, like we're going to be mentioning 8s all the time. Okay, so that's where that terminology comes from. Is that if you see 8 at the end, that means that I've deprotonated my carboxylic acid. Now, because I have acids ready to react and get rid of this H+, if I just throw base at it, they will react right away. This is an important reaction called a carboxylate neutralization, and the result that you get is a carboxylate salt. So in other words, if I react OH minus with this H plus here, because remember, this can split off to become H plus. So this could be H plus, and this could be OH minus. Whereas the sodium is just this Na plus here. What do I get when I combine these two things together? Well, I get water, right? And then the other charge that's left over balances out this minus over here to make my carboxylate salt. Remember that a salt is just an ionic compound? So here's my carboxylate salt. This is just like any acid-base neutralization that we studied in Unit 10 last quarter. Now, this reaction is super, super, super prevalent. Notice that I didn't draw a backwards arrow or anything. This just goes straight to the end. All of the reaction will occur for all of the hydroxide that I put in there. In fact, it is so strong that later on we're going to look at a different type of reaction to try and make, like, say, an amide. But if we're combining an acid and a base to do that, we end up just getting a salt. So acid-base reactions usually are the highest priority reaction. They go first because they have a very high equilibrium constant. To name carboxylate salts, we're not going to do that in this class. You can go back to the rules from 121. I think that's Unit 4. Where you name the cation and then you name the anion with "ide" on it. In this case, the anion is just a polyatomic ion, so you just name its polyatomic ion, which will be some sort of carboxylate salt. Alright, so now what I want to do, let's try and do some examples where we predict the products here. So, first of all, I want to figure out what is the reaction from acetic acid in sodium hydroxide. That's probably easier to just do this here. We don't need this arrow floating around here. So, Photoshop, stop that. There we go. So first of all, we need to draw acetic acid. Remember that acetic acid is the 2-carbon version of a carboxylic acid. So this would be CH3, C double bond O, OH. That would be acetic acid. We got sodium hydroxide, that's this. And then I want to find water. Here's my water. So that's going to be my first product. And then the remaining product would be this sodium ion and this carboxylate anion. So that would be CH3COO minus Na plus. And you can see that acetic became acetate, or acetate is how we pronounce it. In our ionic compound there. I didn't mean to hit that, sorry. I'm doing things out of order here. All right. Now, why do we care about carboxylic acids in terms of biology? Well, acidic things tend to be reactive and, in some cases, corrosive or destructive. So, things that have small amounts of acid in them, such as carboxylic acids, which are weak acids, can kill off stuff like bacteria. Bacteria cannot survive in weakly acidic environments. They need it to be more towards the neutral end. So what we end up using, I can't even speak here. What we end up using carboxylate salts for are food preservatives, because if we add these salts to them and then they're exposed to water, which is what these media would contain bacteria and stuff for, such as moisture in the air, then what would immediately happen is you would form the acid. And then that acid would then react with any bacteria. So a prevalent problem that we end up with is mold on things like bread and stuff. Mold is really susceptible to environments that are kind of sort of moist. So like bread, if your bread goes stale, like it's not going to get moldy super quickly. But if it's like a soft bread, like a roll or a bun or something like that, you can get mold on that fairly easily if you just leave it there for too long. But if you put sodium benzoate in there, then what will end up happening is that when the mold tries to come in there, it comes along with water and moisture. The benzoic acid gets protonated, and then it reacts with the bacterium, and the bacterium or the mold can't flourish. It can't proliferate. I can't words today. I blame naproxen sodium. My back is kind of hurting too, so I might have to get up here in a second. In fact, the doctor told me that every hour I should actually be taking my break instead of sitting here and talking with you guys. So what I'm going to do is I'm going to actually... That's not the break time card. I'm going to actually take my break and get up and go get more water and walk around and just try and be mobile. So I won't be around to answer questions for about the first 5 or 6 minutes. Let me get the Mega Man music back up here. Oh, and the timer. I got to do that too. There we go. So we'll do this, and I'll start the music again, and I will see you in about 10 minutes. I muted the music, oops. Alright, we're back. I got up and walked around, and all the cats chased me. And all two of them. I only have two. So my shoulders feel a little better just because I've been doing like the... I don't know how to describe it other than like if I was a chicken and I was flapping my wings, this is what my shoulders would be doing. Like I'm trying to roll them around in a circle to just try and like flex them. So if you hear like, I don't know, like static or something, that's just me trying to like flex my shoulders. Just because I know that the mic picks up like weird like sounds of motion and movement and stuff like that. All right, so let's talk a little bit about esters today. So we've seen pretty much all the simple stuff that carboxylic acids will do. What we are going to do now with them is react them to make esters, and then we're going to talk about common properties that esters have. Now, you've probably heard of an ester and just didn't realize it. For example, polyester. I don't know why you would be wearing something made of polyester. Maybe it's the 70s. I don't know. But polyesters are esters. And we're going to talk about all about that coming up. All right, how do you make an ester? The easiest way to do this is to take a carboxylic acid and react it with an alcohol. And when you do that, the following happens. Like with most reactions that we do that are interesting, one of the products that we make is water. So first you got to find water. Oh, there it is. So we're going to make water. And then the second thing that happens is that I take all the remaining parts and I just kind of connect them together. So we're going to go, I'm going to connect these two things together. And when I do that, I get this result. So there's my water over there on the side. And then I have, here's my propanoic acid part. We'll box that in there. And then let me get a different color out. We'll do green. Here's my alcohol part. My ethanol part, I guess I should say. And there you go. Now, what do you need to do this? You need to have a source of acid. So this reaction is acid catalyzed. And you generally have to heat the reaction up hot enough so that this will happen. So it takes a while. I'm trying to pet the cat to keep her quiet, and she's just looking at me and going, rah, rah. I'm also trying to train Maya to say hello. Hello. Well, she won't say it. Okay. Of course, like, she's going to be like, meow, meow. And that'll be close enough to hello that I will be super enthusiastic for her. Oh. I had to show our ester in here, so let me go back here. There's our ester right there. Here's the C double bond O with an O coming out to the side, and that O is connected to an R group. So here's my R group. And this is some other R group. So when you look for an ester, you should look for that linkage. Now, presumably you already know that because there was a slide very, very, very early on that said, here's every functional group. So you know what you're looking for in an ester when you see that on the screen. Or should, anyway. How do you name esters? Let's go back here to this slide real quick, and we'll talk about the naming scheme for our esters. All esters are synthesized from a carboxylic acid and an alcohol. Now, there are other ways to make them, but you could imagine that any ester could be constructed from these two parts. When you name an ester, you are going to name the two groups that are present in this order. So the first is going to be the alcohol. And you're going to name its chain. So here, this is just ethanol, so it would be an ethyl group. And then second, you're going to name the carboxylic acid. Wow, that could not look more unusual. Let me try that again. Carboxylic acids. We're going to name it as an anion. In other words, what this would be named as if I had deprotonated it. So since this would be propanoic acid, as an anion it would be propanoate. So what I would call this would be ethyl propanoate. That would be my ester. Let's do another one. Let's do all sorts of these. So, for example, here we've got this group right here. Excuse me. You could imagine that this molecule came from these two reactants. So first I've got this. This would be my carboxylic acid. And then this would be my alcohol. So if I did that and I named it in this order, first I would name whatever the group was that came off of my alcohol. So that's phenyl. And then I would name whatever this is if it was deprotonated. And so that would be propanoate. And so that's what this is. We'll clear all that out because the slides do it neater. So that's how you name these. Name the group that's on your alcohol. Name the carboxylate part of your carboxylic acid. All right. What would I call this? Now you're going to start seeing weird groups in here. We've used them on the worksheets, and I think I've introduced them like maybe once or twice on the slides, but just be mindful that they exist. I'm going to start throwing them at you so that you'll see them on the exams and stuff. So now she's actually saying hello. Maya, stop. Oh my goodness. So what would I call this? Type its name in the chat while I deal with the cat. All right, so this is not an isopropyl group. So isopropyl looks like this. There's an extra one in here. So this group's actually called tert-butyl or tertiary butyl. And you can think of it as, if this is my R group over here, I'm bonding it to a carbon, which is bonded to another carbon, another carbon, another carbon. And these all have H's on them. And so just like a tertiary alcohol would be something like this, you can think of this as just a tertiary butyl type group. Okay, Maya, you need to stop. It's time to squirt bottle the cat. All right, so this is tert-butyl. Another abbreviation you might see for that is T-butyl. And then this is, there's 4 carbons, so that'd be butane. But if it were an acid, we'd call it oic acid. If it were an anion, we would call it O8. So the name that I would give for this would be tert-butyl butanoate. There you go. So you're close on the anion, but had the wrong alcohol group. That's right. We're not naming the alcohol. We are naming just the R group. That's what this is. So if it was propane, you would literally name it propyl. Not propanol, but just propyl. So let me do it this way. So step 1, name this R group. And then step 2, name this carboxylate. And you do that for any ester. Name the R group on the alcohol side, name the carboxylate that's left over. In fact, if I'm going to do that, let me redraw this box here. So it includes this O here. There you go. Try that. If that algorithm works for you, then that's great. All right, let's name more of these. So I want you to follow that algorithm. 1, name the alcohol R group. And 2, name the carboxylic acid as a carbonate. Carboxylate. Now be careful. You'll notice that I always have these oriented where the C double bond O is on the left and the O is on the right. I could, in theory... In fact, I'll just give you a third one here. We're going to flip this guy around a little bit. And you still follow the correct rules, but you just have to be mindful that you don't accidentally name it something weird. So we'll go like this. Doot, 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 doot. Doot, doot. Sure. All right. Go ahead and name these 3. And we'll go over the answers in just a second. 1 or 2 more minutes to go over the, and we'll go over the answers. All right, let's go over the answers here. So we'll write the directions up at the top again, same as I had on the last slide here. So 1, I could just misspell alcohol as alcohol. Lol. Alcohol are group to name the carboxylate. There we go. All right, so this would be step 1, and this would be step 2. So what I circled in 1 is isopropyl. And then in step 2, I circled benzoic acid, but it's not a carboxylate acid, it's a carboxylate. So it'd be benzo 8. There you go, isopropyl benzolate. Benzoate. All right, same thing over here. So this would be 1. This would be 2. So 1 is just phenyl. 2 is ethanoate. You could also call it acetate here. I'm going to put ethanoate just to be consistent with the rules that we're using. But if you called this phenyl acetate, and I'll even write that. That would also be okay. And then down here, I just did it backwards. So this guy is on the left, so this is 1. And then here is my carboxylate. So we will call group 1 is what? Butyl? Yeah, butyl. And then this is 1, 2, 3. This would be propanoate, but it's got a methyl group on here. So this would be butyl 2-methyl propanoate. Propanoate. There you go. All right, that's how you name esters. Hopefully we worked out some of the kinks there. Because I realize that these naming conventions are just getting more and more convoluted and ridiculous. And when we get to amides, it'll be even worse. Let me know if you have any questions, though. Oh, look, I have more problems for you because I didn't hit the spacebar, so we'll just go like this. Oops. I want you to draw these esters out for me. So draw ethyl ethanoate, and then draw isopropyl pentanoate. I'll give you 3 or 4 minutes to do that. I think it's easier to turn the names into a picture, because you know what goes where. You can also orient it in either direction you want. So you can have the alcohol part be on the left or the right, however it works out. Okay? Go ahead and draw these. I'll check back in with you in 3 minutes or so. All right, have we drawn the structures? Let's go over the answers. So for ethyl ethanoate, we'll draw the ethyl group first. I'm going to just draw it in this orientation. So we'll start by drawing this. And then we'll draw the ethyl. So there we go. And then ethanoate. So I've already got one carbon here. We'll just draw a second one. There it is. And then for isopropyl pentanoate, we'll just start here. So we'll do isopropyl. Boop, boop, boop. There we go. And then pentanoate. 1, 2, 3, 4, 5. There you go. All right, what can esters do? Let's play around with some ester physical properties. Now, esters can't hydrogen bond to each other. So what that ends up meaning is that if I go back and look at my ester here, the really only interactions that I have are going to be dipole in nature. So if I have 2 esters interacting with each other, 2 copies of this molecule, for example, they're just going to have their dipoles interact. And so most esters end up having much lower boiling points than carboxylic acids do. But if we go back to that picture again, and we look at all the places where we can hydrogen bond to from, say, water, well, I could just do this. There's a hydrogen bond, or I could hydrogen bond here or here. There's 2 electron pairs, so there's all sorts of places I could hydrogen bond to an ester. So esters that are small enough and have few enough carbons end up being soluble in water. So a really common ester that is very soluble in water is called ethyl acetate, and it's used as a solvent. And this is just ethyl ethanoate, which we wrote on the other side, or the other slide on the previous ethyl acetate, also known as ethyl ethanoate. And this is a liquid at room temperature. It has a very low, what am I saying? It has a very low boiling point. And it's pretty polar. It mixes well with water, and it smells god awful. I hate the smell of ethyl acetate so much. And I can't even tell you what it smells like because it's impossible for me to really describe or remember. But as soon as I walk into a lab and I smell, I'm like, that's ethyl acetate, gross. So, you know. All right. When you make an ester, you make this thing called an ester linkage, which, as you can see right here on the screen, isn't there. So I'm going to hit the button here. There you go. When you connect the O of your alcohol to the carbon that is in the carbonyl group, the C double bond O, you create the ester linkage. That is the linkage responsible for forming the ester. Now, this is going to be important later on because when we make fatty acids into triglycerides, we're going to link the fatty acids to glycerol by doing ester synthesis. We're going to create esters. And so those linkages will be ester linkages in triglycerides. Ester linkages are fairly strong. However, they are susceptible to hydrolysis, which means that if you have water and a source of acid, or in some cases a source of base, you can create you could create a situation where your molecules will break apart into carboxylic acids and alcohols again. So we're going to spend a lot of time in this chapter talking about esterification and how to undo it with water and acid and stuff like that. Now, where do you find esters in the outside world? You find them in things like fruits and plants. Anything that has like a fruit taste or smell to it tends to be an ester. There's a really cool lab that we would do if we were in person, where you get to make artificial fruit flavoring. And you get to smell it, and so you make this molecule, and it's like, oh, that smells like grapes. And you make this, oh, goodness. The names are all common names, unfortunately, so I don't actually know what they're, like isoamyl acetate. I don't know what isoamyl is. That's, but I believe that one is the banana smell. So, like, you do the synthesis, and then you take a sniff from your tube, and it's banana. And then there's one that never works, and I think that's pineapple, which is unfortunate because I love the smell of pineapple, but that reaction's not very good. But we do grape, we do strawberry, and so esters tend to have very fruity and nice smelling scents. For whatever reason, the exception is ethyl acetate. It smells like garbage. So some esters don't smell nice, and that's because they are typically components of fats and oils. Some fats and oils do smell nice. So like coconut oil smells good to me, but like, yeah, that's really all I can say about that. I was like, well, wait, butter smells good too. What's the bad part of butter? That's actually a carboxylic acid that comes out. All right. How do we make esters? Again, we're going to combine carboxylic acids with alcohols. Now, unfortunately, this reaction ends up being reversible. And so what ends up happening when we do this reaction is I can make the ester linkage, but the water is already there. And so if this acid that's already present as my catalyst finds this, and my water comes in to break this bond, I end up with my starting materials again. So this reaction is doable. However, we don't get a lot of ester out of it. We're going to use this reaction to do things like fatty acid synthesis. We're going to do stuff with carbohydrates in it. Later on, when we talk about proteins, proteins form amide linkages, which is essentially esterification with an amine instead. But this process is very common to make these linkages and then break them apart. All right, so let's predict the products of this reaction. So, assuming that we create the ester, which we can, we're just not going to get it in very high yields. We're going to indicate that with this double arrow here. What is the product? So, whenever you do an esterification, first thing you want to do is find water. So, here's my water. And then I'm going to connect the rest of the molecule together. There you go. So, let's just draw what I just did here. So, CH3, C double bond O, O, and then that's going to connect to a phenyl. That should be our product. And if I advance the slide, totally is. Now, you do make water as a product. We don't ever need to include the inorganic products on these problems that I'm going to be giving you, because this is organic chemistry. We don't really care about water. So we're just going to ignore it. For the purposes of understanding why the reaction is reversible, though, noting that water is there is useful. But if I ask you, what is the product of this ester synthesis? Just give me the ester. All right, so here's two more of them. I want you to predict the products. You don't have to include water because nobody cares about water. And when you're done, let me know, and we'll go over the answers together. You don't have to name them, but if you can, go ahead and do so. All of these are nameable. It just looks like that first one looks kind of weird. So I'll just tell you what group this is. So this is a sec butyl group. Right here. All right. Go ahead and do these syntheses and draw the products. All right, let's go over the answers, and then I think we'll call it a day here because I don't want to jump into the next part of the topic with only about 5-10 minutes left. So, all right, so we're going to first find water. So here's my water. I'm just going to scribble out the water, and then I'll connect the rest. So we'll go do 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 O do 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 do. So that's what your molecule should look like. And then to name it, we would name the alcohol group first. So this would be sec-butyl. And then I would name the carboxylate part. 1, 2, 3, 4 would be butano-8. I'll get rid of those underlines here just because it's a little unclear. Same thing over here. Let's find water. There it is. Connect the rest. And I would get a mess if I do that. Do, 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 do. That's the sound you make when you draw organic structures, I guess, is do, 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 do. And if we had to name it, we would name this part first. So you can name the alcohol first. That would be phenyl. That's the R group on the alcohol. And then the carboxylate part would be benzoic acid, which would become benzoate. There you go, phenyl benzoate. That is how you name esters and create them from simple carboxylic acids and alcohols. Any questions, let me know. Let me check really quickly just how many slides are in this section real quick. I guess I could spend a few minutes talking about polyesters real fast. So now that you've seen how do we make an ester, you can make a polyester by doing this reaction infinitely. And you might ask yourself, well, wait, how the heck would you do that? And the answer is, well, I need to have an alcohol that has 2 alcohols on it, so a diol, and something with 2 carboxylic acids on it, and I could just chain from either side and do that forever. So an example of that would be, don't worry about this slide here, would be something like this. So here I can make a connection here where I kick off the water. So there would be my water I kicked off, and then the rest would join together. And then I could connect this side to the same molecule. And I could connect this side over here to another carboxylic acid. And I would just repeat alcohol, carboxylic acid, alcohol, carboxylic acid, alcohol, over and over and over until I had polyester. So I believe that I show that here. So here is one ester linkage that is formed, but I could potentially make another one here and another one here. And then just plop down the other molecule that I need. So I would alternate between the diol and the dicarboxylic acid. Now, in the previous slide, it just talks about what this is called. So this type of reaction is called a condensation polymerization because what you are doing is you are condensing water out of it. Because every time you make an ester linkage, you kick off a water molecule. And so if you do that enough times, you eventually get a lot of water. So we call it condensation. Because we're gathering all the water in one place out of the molecules, I guess. I don't know, something like that. So polyester, which is a type of clothing, is formed in this manner. Now, later on, what we're going to learn is that if you have polyester clothing, you have to be careful about wearing it in an environment that is subject to acid or base. So you could not choose a worse clothing to bring to the lab than polyester, Because if you spilled acid on yourself and it was sufficiently warm, then what would happen is your clothes would not only fail to protect you from the acid, they would actively melt when exposed to it. And that could cause further injury because it's harder to clean off something that's melted on you than it is to just take off a piece of affected clothing. But we'll cover that in more detail later on when we talk about hydrolysis of esters, which will be next time, probably on Tuesday. Before we call it a day, I do want to check the calendar really quickly. Is week 7 the day that we have off for President's Day? So, academic calendar. Always the top search in my Everett Community College. Because there used to be a link to it on the front page, and now there's not for some reason. February 15th is President's Day. Yeah, so next Monday there is no class. So there's no Q&A, there's no lecture. I'm not going to post anything because it's a school, campus is closed. So please enjoy that. You do have a lab coming up, lab worksheet number 3. And that'll be the only thing due next week because we're not going to put quiz number 15 up until we are done with this chapter, which we're about a third of the way through, maybe almost a half. Be mindful that when we get to the biochemistry part, the chapters start finishing a lot more quickly because there's less content. But the topics are also as varied and diverse as like the stuff that we've covered so far. So just be mindful of that. Otherwise, have a wonderful weekend. I'm going to try and figure out all the exam snafu stuff on Canvas tonight. So I will post an announcement when that has been done. Until then, take care and have a wonderful weekend. And we'll see you next time.